So, have you ever actually stopped to wonder what keeps the massive, modern digital world from just completely collapsing under its own weight? Well, today we are cracking open the ultimate survival guide for catastrophic network meltdowns. Throughout this explainer, we're going to explore the invisible rules that dictate how our data flows, how networks literally heal themselves, and how we can actually cheat the physical limits of our hardware. Let's dive right in. I want to kick things off with a question that might sound honestly a little crazy. Can plugging in just one innocent-looking redundant backup cable destroy an entire network? Well, the short answer is absolutely yes. In fact, if you plug in a backup cable without the right protocols in place, you can trigger this infinite loop of data that will literally melt down your entire network infrastructure. To understand exactly how a single cable can cause that kind of disaster, and more importantly, how we stop it, we really need to start at the foundation of how network traffic is organized.
All right, Section 1, Slicing Traffic with VLANs.
Before we can understand how networks break, we kind of need to look at how we organize a chaotic digital city into neat, manageable neighborhoods. Imagine you're in a massive office building, and every time someone wanted to talk to someone else, they had to use a megaphone. That is exactly what a network without VLANs looks like. It's just a massive, noisy broadcast domain where every single broadcast frame is heard by every single device. But virtual LANs, or VLANs, allow us to logically slice one physical switch into multiple invisible, isolated switches. So now a broadcast sent in one VLAN stays completely contained within that specific neighborhood.
This invisible segmentation is basically a network engineer's best friend. It gives us massive real-world benefits. First off, it frees up CPU power because computers aren't wasting processing cycles discarding all those irrelevant megaphone broadcasts. It also drastically tightens security by keeping, say, the accounting department's traffic completely walled off from the engineering team. You can group users logically by their department, regardless of where they actually sit in the building. And crucially, it shrinks the failure domain. If something goes wrong, the fire is contained to one VLAN instead of taking down the whole building.
But how do we scale this whole thing? When these VLANs need to travel between different switches across a huge campus, we obviously don't want to run a separate physical cable for every single neighborhood. Instead, we use a process called IEEE 802.1q trunking. This protocol dynamically injects a tiny 4-byte header into the Ethernet frame right before it crosses the link. Tucked inside that header is a 12-bit VLAN ID. Think of it like a VIP pass that tells the receiving switch exactly which neighborhood the data belongs to, keeping everything perfectly separated, even when it's all sharing one single physical wire.
Which brings us to a pretty major dilemma. If all our traffic from multiple VLANs is riding over a single trunk link, what happens if a backhoe cuts that fiber cable outside, or a switch port just randomly dies? We lose everything. So naturally, to survive a failure like that, you have to plug in backup cables. But remember that crazy question I asked at the very beginning? Here is the catch. Plugging in redundant backup cables physically creates a loop.
And loops in Ethernet are absolutely deadly. Without some sort of traffic cop to manage these redundant links, a single broadcast frame is going to be flooded out of all ports, received by the other switch, and flooded right back. These frames will circulate infinitely, multiplying exponentially into what we call a broadcast storm. In just a matter of seconds, this storm will max out your switch's processors and completely paralyze the entire network. You are literally dead in the water.
So, we need a hero to fix this. Section 2, Stopping Loops with STP. To save us from this catastrophic meltdown, we rely on the Spanning Tree Protocol, or STP. STP prevents loops by running what is essentially a digital political election to establish a single point of reference for the whole network. Here's how it goes down. Step 1. Every switch powers on and stubbornly claims to be the supreme leader, the root switch. They announce this by sending out messages called Hello BPDUs. Step 2. They start comparing their bridge IDs. If a switch hears a lower, or technically speaking, a better bridge ID than its own, it immediately concedes and drops out of the race. Finally, in step 3, everyone mathematically agrees on one single elected root switch. Okay, so once the root switch is elected, every other switch calculates its absolute fastest path to that route. We call this its root port. Then, on every individual network segment, the switches elect a designated port to forward the actual traffic. And what about those redundant backup links that aren't immediately needed? Well, STP ruthlessly blocks them. It completely disables the port for user traffic, physically breaking the loop and creating a strict, loop-free mathematical tree. So STP successfully saves us from broadcast storms, right? We have our backup cables plugged in, and STP is blocking them so they don't cause loops.
But this strict traffic cop creates a brand new nightmare. What exactly happens when a primary link actually snaps, and we desperately need to activate that blocked backup cable? 50 agonizing seconds. That's how long old-school STP can take to unblock a backup cable. It wastes 20 seconds just verifying a link is actually dead, using a max age timer. And then it awkwardly transitions through these 15-second listening and learning phases before it finally starts forwarding data again. In a modern network where we expect instant loading times, a 50-second outage means dropped video calls, corrupted file transfers, and pretty much complete chaos. 50 seconds is an absolute eternity. Section 3, speeding things up with RSTP. To fix this massive delay, the IEEE introduced Rapid Spanning Tree Protocol, or RSTP. If we compare how they manage ports, you can see RSTP simplifies everything. It takes the old, cumbersome blocked states and bundles them into a single, clean, discarding state. And it completely deletes that agonizing listening phase. Instead of just passively waiting around for fixed timers to expire, RSTP is actively designed to communicate with neighboring switches to negotiate transitions right away. But the real secret here is that RSTP introduces this brilliant pre-calculation. While the network is totally healthy, it's already planning for disaster. It mathematically calculates alternate ports, which act as immediate backups to the root port, and backup ports. Because it's already done all the math ahead of time and knows exactly which port is going to take over, if a primary link fails, RSTP can transition an alternate port to forwarding almost instantly. No more 50-second blackouts, just immediate, seamless failover. Okay, so now we have a fast, loop-free network with instant failover. But here is our final complication, and it's a big one. Even with Rapid STP, the protocol is still actively blocking our really expensive backup cables to prevent loops. This means if you buy two 10-gigabit fiber links, you only ever get to use one of them at a time. So how do we use all our cables simultaneously without causing a catastrophic loop? Think about those thick bundles of cables running through a modern data center. Leaving half of those cables sitting completely idle just in case a primary link fails, that's a massive waste of money and bandwidth. We desperately need a way to combine the speed of these parallel links, which brings us to a highly clever solution. Let's bend the rules a bit. Section 4, EtherChannel. EtherChannel essentially lets us completely trick the spanning tree protocol. By configuring a port channel, we can bundle up to 8 physical cables together. STP looks at those cables, but EtherChannel casts an illusion. STP only sees one massive pipe. And because it only sees one link, it thinks there's no loop. That means all the cables get to actively forward traffic at the same time. We dynamically negotiate this bundle using protocols like LACP or PAGP. Then the switch uses some really clever math against the MAC or IP headers to perfectly balance the data across all the wires. And the absolute best part, the real magic tick, if a backhoe snaps just one wire in that bundle, the other wires instantly take over. STP doesn't even notice the change. 0 loops, 0 downtime. EtherChannel fundamentally changes how we scale bandwidth and redundancy. By virtualizing our physical layer, we took a network-destroying loop and completely transformed it into a massive, highly resilient highway of data. And honestly, that leaves us with a fascinating question to wrap up this explainer. If we can virtualize our cables to cheat physical limits and completely trick our protocols, how far can we push virtualization across the rest of our hardware? I mean, could we trick the network into thinking 2 completely separate switches or actually just one? Keep that in mind the next time you look at a modern data center, because the physical reality is almost entirely masked by brilliant logical engineering. Thanks so much for joining me, and keep exploring.